Okay, today's lesson is concerned with the graphs of trigonometric functions. There are three main trig ratios. And they are sine theta equal to opposite over the hypotenuse, tan theta equal to the opposite over the adjacent, and cos theta equal to the adjacent over the hypotenuse, where we have a right angled triangle. Our angle is theta. We have our opposite, our adjacent, and our hypotenuse sides. Now, this type of trigonometry is only concerned with angles between 0 and 90 degrees because it's restricted to the size of the angles that can fit into that right angled triangle. But what if we were interested in angles that were greater than 90 degrees? Well, what we can do is we can transfer our right angled triangle to a coordinate plane, and in that way we would be able to look at angles that are greater than 90 or also negative angles as well. So I'll just write that up and we'll have a look at what that means. Okay, so here's the right angle triangle that we had in the previous slide. There's theta, our opposite, our adjacent, and our hypotenuse. What we're going to do is we're going to take a coordinate plane and we're going to add that right angle triangle in again there. So there's theta. We're going to make the corner a point P. We're going to give it a coordinate x, y. So that means that it's x along here and y up. That's x on the horizontal and y on the vertical axis. And if we were to say that point P is a point on the circumference of a circle, we could create a circle here. And as theta, the angle, changes size, point P will move round the circumference of the circle. And that means that the coordinate for point P will change because the x value will change and the y value will change. I'll write that bit of information on the next slide, but I'm just going to carry on writing on this slide at the moment. So basically, now that we're on a coordinate scale, x can be negative and y can be negative. So we can have points in any of the four parts of the coordinate scale. Now, if we want to write our three trig ratios in terms of this coordinate scale now instead of the right angled triangle, then what we will need to do is we will need to find some sort of measurement for the hypotenuse. And hopefully you can see that that's a radius of the circle because it's coming from the centre of the coordinate plane out to the point P on the circumference. So that's a radius of the circle, and it's also the hypotenuse of the right angled triangle. So we can now write the three trig ratios in terms of the values on this new diagram. So we have sine theta. So that's the opposite over the hypotenuse. So in this case it is y over r. For cos, we've got cos theta. That's the adjacent over the hypotenuse, so that's x over r. Finally, we have tan theta, and that there is the opposite over the adjacent, so that is y over x. Now, the only other thing we might want to do is to add in some values for theta. So we tend to start here with our coordinate scale. We call the x-axis 0 degrees. So theta would be 0 if the line r, the radius, was lying on the x-axis. And as theta starts to increase this way, in an anti-clockwise direction, then we would come round to 90 degrees, 180 degrees, 270 degrees, and finally we've gone a full circle, we have 360 degrees. Theta can actually, on this coordinate scale, go in the clockwise direction as well, which would give you a negative angle, and that's explained on the next slide. So now, as angle theta changes, the point P, which is the coordinate xy, moves around the circumference of the circle and each angle gives a new unique point P. Just again say the angle can be positive, which would be in an anti-clockwise direction, or negative, which would be a clockwise direction. I'll just show you that on the next slide. So if that is our scale, this could be angle theta reading in this direction, so that's positive, or it could be coming down this way, so that would be negative. Now, overall, this is going to help us to find values for angles for any point of P. So any x values and any y values. I'll give you an example of that. Okay, an example. So we have a point P, we have a radius r if we take a line from the centre out to P. X is 4 and y is 3. So first of all, we'll need to find out what r is before we can work out our sine, cos and tan ratios. So we need to know our hypotenuse of this right angled triangle. So we use Pythagoras' theorem. So to do that, we would have r squared is equal to 4 squared plus 3 squared. So r squared is equal to 16 plus 9. So we have r squared equal to 25, leaving us with r equal to 5 when we take the square root. So we now know the three sides of the right angle triangle, and we can use those sides to write down values for our three trig ratios. So we can have sine theta. Sine theta was the opposite over the hypotenuse, so it must be 3 over that radius value of 5. Cos theta, well, that's the adjacent over the hypotenuse, so we're going to have 4 over 5. And finally tan theta, which is the opposite over the adjacent, so we're going to have 3 over 4. And we'll look at a second example. Okay, this time you can see that point P has gone in the negative x direction and the negative y direction. So our angle theta actually comes all the way around here from the positive direction of the x-axis. So it reads all the way around to here. And if we think about our y value, that's -5, and our x value is -12. So we need to do the same thing and find out a value for r by Pythagoras, and then we can use those 3 sides to find out our trig ratios again. So we have r squared equal to -12 squared plus -5 squared. There we go. So what I've done there is I've put brackets around the negative signs, just because in the calculator it can get a little confused, and a negative squared should be a positive. If you don't get a positive value in your calculator, it's because you've not included those bracket signs. So we've got r squared is equal to 144 plus 25. So r squared is equal to 169, meaning r is 13. So we can go ahead and look at our ratios now. So we have sine theta. Sine theta is going to be opposite over the hypotenuse again, so that's -5 over 13. Cos theta, adjacent over hypotenuse, so -12 over 13. And finally, tan theta, well, that would be -5 over -12. However, a negative divided by a negative becomes a positive, so we have 5 over 12. And you could work out what the size of those angles were in the last 2 examples by taking the inverse sine, inverse cos, or inverse tan to get theta. We can use these definitions of the 3 trig functions to sketch the graphs of each function. But first we need to redraw our circle on our coordinate plane with something called a unit circle. So let me just write this down for you. We can use these definitions of the 3 trig functions to sketch the graph of each function. First we make the radius of the circle equal to 1. To give a unit circle. And I'll draw that on the next page. Okay, so we have drawn our circle on our xy coordinate plane. We have produced a point P on the circumference of the circle that is made by an angle theta, so we can call that P theta. The radius of the circle is 1, so this is our unit circle because it has a radius of 1. And you can see that point P has a coordinate x and y, so that produces our right angle triangles that we've been looking at there. And depending on the value of x and y, obviously we would have a different angle of theta. Now, what we add on to here is some way of measuring round our circle, and we're going to do that with degrees. So this line here, which is the positive direction of the x-axis, we would call that 0 degrees. And if we move round the circumference of the circle, we get to the positive direction of the y-axis, and that would be 90 degrees at that point. And that's a right angle there, so that's why it's 90 degrees. If we come round to the next axes, we have 180 degrees. Following round, we would have 270 degrees. And finally, when we come back full circle, we have went 360 degrees round in that circle. So we know that any angle of theta between 0 and 90 would be here. If our angle is greater than 90 but less than 180, our position point P would be somewhere in this quarter here. Again, P would be here if the angle is somewhere between 180 and 270. And then finally P would be here somewhere in that section of the circumference if the angle is between 270 degrees and 360 degrees. Now, if we look at our three trig ratios now, we can see what happens to them based on a unit circle. So we have sine theta. Now sine theta, remember, is the opposite over the hypotenuse, so that would be y over 1 in this case, so really we've just got y. So what we can say there is that the sine of the angle is a vertical displacement. And displacement just means a distance moved. If we look at cos theta, this time we're looking at the adjacent over the hypotenuse, so that would be x over 1, so just equal to x. So that is the horizontal displacement, which hopefully I can fit in here. Doesn't want to write that. Nope. Here we go. Not great, but it's there. And I'm going to have to go on to the next slide to be able to fit in tan theta. But tan theta is going to be the opposite over the adjacent. So we're going to have y over x, which I'll write next. So tan theta, we said, was y over x. So that is our three trig ratios, or three trig functions that we were looking at previously, but now when we have a unit circle they change to this, and it's important for the sine and the cos that the sine is the vertical displacement and the cos is the horizontal displacement, and that helps us when we come to draw the three graphs. And the first graph that we're going to look at is going to be the sine graph. Okay, so the sine graph, we're going to start with that unit circle again. And what we're going to do is we're going to move round the circle, taking different sizes of angles and finding out what the y value would be. So this time we have an angle, theta, and we're interested in what the y value would be. And that will help us to produce a graph of the function. So the graph will go on the axes here on the right hand side. So we're going to look at, well, 0 degrees, 30 degrees, 60 degrees, 90 degrees, and we're going to continue round in 30 degree intervals. So that would be 120, 150, 180, 210, 240, 270, 300, 330, and then we'll be back to where we started with, which would be 360 degrees. Once we have the y values for these, we can plot them on the graph and see the shape that the sine function produces. So on the calculator, to get these values, if you wanted to know what the sine of 0 was, you would press your sine button in the calculator, put 0, press equals, and you find that the sine of 0 is 0. So that gives us a point here. Do we know that? We'll just put in some values here. There we go, that'll come in a minute. So then the sine of 30 would be sine 30 in your calculator, and you find that that is 0.5. So I will just add a couple of bits of information to this graph so that I can try and draw it accurately, which is difficult when you've not got graph paper. So really we're doing a sketch. Okay, so 30 will be in here somewhere, so we'll make that half. We do the sine of 60, we get 0.866, so we will put that in there. And finally, the sine of 90 gives us 1. Oh, 2 dots, I only really want 1 dot. There we go. And then we'll carry on between 90 and 180, so 120 is also 0.866. The sine of 150 is a half. And then finally, the sine of 180 is 0. So you can see that really the same values have just been repeated there again. This time first time we were increasing between 0 and 90, and now we've decreased back down to 0 between 90 and 180. And we'll continue on. So we have the sine of 210, and that is minus 0.5, sorry, so that will be an error. The sine of 240 is minus 0.866. And the sine of 270 is minus 1. And continuing into the last three values, we've got the sine of 300, which is minus 0.866 again. The sine of 330, which is minus a half. And finally, the sine of 360 is 0. So again, a pattern forms there. It's the same numbers, but sometimes they're positive and sometimes they are negative. Now, if we combine those dots together, you get this shape here. So you can see that it's increasing, coming down to 0 again, right down to -1, and then back up to 0 again. And this is the graph of y is equal to sine theta, or y is equal to sine x. You might have seen that written. So on the next slide, we will have a look at the key points on this graph. So the key points are 0, 0, 90, 1, 180, 0, 270, -1, and 360 is 0. So the coordinates, basically, the x coordinates are the angles, and the y coordinates are the values. So 0, 1, -1, the height of the wave on the graph. And then we have the amplitude, which is the height. That's equal to 1. And we have the period, which is the length of one wave. That's equal to 360 degrees. So they're the key points for a sine wave. Now we will do the same for the cosine wave. Okay, now we're going to look at the cosine graph, and again we need this unit circle. And we'll draw a graph on this axis here, so we'll put in our values that we need again. And we're going to take the same intervals, so we're going to have 0, 90, 180, 270, 360, and all of the 30-degree intervals in between, so 30, 60, 90, and so on. Okay, so again, to use the calculator, you would do the cos of, say, 0, write that in the calculator, and in this case what we get is we get 1. So the cos of 0 is 1. Moving round, the cos of 30 is 0.866. Now that number's familiar because it was a number that was also in the sine wave, although it was the value for the sine of 60, in this case it is the value for the cos of 30. So there is a relationship between these two graphs, and we'll explain that at the end. When we take the cos of 60, we get half, and the cos of 90 is 0. And we continue on. So for 120, we get minus a half. For 150, we get minus 0.866. For 180, we get minus 1. For 210, it's minus 0.866 again. For 240, we get minus a half. And for 270, we have 0. And then the last three. For 300, we get a half. For 330, we get 0.866. And for 360, we're back up at 1 again. And if we try and produce that shape, oh, I've missed the dots completely, but that is more like what the shape should look like. As I said earlier on, it can be difficult to draw these graphs when you haven't got graph paper and you're just trying to do a sketch, but that's really what the shape of the cosine wave should look like. So this time it starts at 0, at 0, start again. This time it starts at a height of 1 when the angle is 0. It comes down to a height of 0 at 90 degrees, carrying down to minus 1, back up to 0, and then continuing back up to 1. So it starts at a height of 1 and ends at a height of 1. And we'll say that is the graph of y is equal to cos theta, or y is equal to cos x, whatever you're calling your angle there. And again, on the next slide, we will have a look at the key points. Okay, so the key points on this graph: 0, 1, 90, 0, 180, minus 1, 270, 0, and 360, 1. So again, the 0, the 90, the 180, the 270 and the 360 are the angle, whether that be x or theta or any other name you want to call the angle. The 1, the 0, the minus 1 are all heights. Again, if we look at the amplitude, remember the amplitude was the maximum minimum heights, so it goes between 1 and minus 1. So the amplitude is 1. And the period, we said, was the length of one wave. So one complete cycle of the cosine wave is between 0 and 360. So the period is 360 degrees. Now, as I mentioned, these two waves are related to each other. And why do I keep using the word wave? Well, really, that's what the shape is. So we often describe the graphs of sine and cos as waves. And when we actually look at them, we can see that they are the same wave because they are the same shape, but they are out of sync by 90 degrees. So on the next slide, I will try and show you that really it is the same wave, just out of position from each other, and it's by 90 degrees, and we call that a phase shift. So I'm going to actually now quickly just sketch them. So if I show you, there's the sine wave. So I haven't put any values in there, I've just done the shape. And if I go for the cos wave over the top, okay, so that's the sine wave and the cos wave on top of each other. I'll just try and add in a few values here. So that would be 90, there would be 180, 270, and 360 degrees. So they have that same wave shape, so they're going up and down, peaks and troughs. But what you can see is that for the cos wave, it starts at the middle height, so that's 0, whereas the cos wave starts at 1, so the sine wave starts down at 0, cos wave starts at 1, and they are changing in position over the 90-degree periods. Okay, so at 90 degrees, the cos wave is now at its lowest point, but the sine wave is now at its maximum point, and they keep alternating shape. However, they are the same wave, just out of sync. So let me write that. Sine and cosine graphs are the same wave, but out of sync by 90 degrees. And this is called a phase shift. Right, finally we are going to look at the tangent graph. And this graph is very different from the sine and the cos, so it isn't related to them in the same way. It's not the same wave out of phase like the sine and the cos wave are. So you'll see that when we produce it. So we'll start with this unit circle again. Oh, not a very good circle there. So we've got 0, 90, 180, 270, and our 360. And again, we'll take 30-degree intervals. Right, so the tan of 0 works out at 0. When we take the tan of 30, we get 0.577. So we will go for about there. When we take the tan of 60, we get 1.732. So already we're looking at already we're looking at the fact that these numbers are different from what we've seen in the sine and cos wave, because we didn't have any y values that were greater than 1 on those two waves. That's because the amplitude was 1, the maximum height was 1. But here we had a value of 1.77, and if we took another angle somewhere between the tan of 60 and the tan of 90, we would find that that number was even greater in terms of y. So this graph is not going to look like the sine and the cos wave. Now, when we take the tan of 90, we actually get an error on our calculator, so that was equal to 0. The tan of 90, error. Okay, so the tan of 90 doesn't actually exist. So what I'm going to do is draw a dotted line there, and we'll explain what that is at the end. Now, if we take the tan of 120, we get minus 1.73. So now we're starting to see a bit of pattern again there, because that is a repeat of the value for 60. However, it's a negative value, so we'll put that in there. We take the tan of 150 and we get negative 5.77. The tan of 180 is 0. Then we have a look at 210. And we are going to get 0.577 again. So we'll try and match this up over there. There we go. And 240, we get 1.732 again. And when we take the tan of 270, we get that error again. So again, another dotted line. And into the last section, so the tan of 300 is minus 1.732. The tan of 330 is minus 0.577. And finally the tan of 360 is 0. So even when you look at those dots, you can see that something very different is going on with the tan wave. If we start to try and draw them like this, and there we see the graph of y is equal to tan theta. So now I'll point out what these dotted lines represent in the 90 and the 270 positions on the x or theta axis, and then we'll also talk about some of the key points of this graph on the next slide. So first of all, at 90 degrees and 270 degrees, the graph does not exist. So there are no values, no y values that correspond to an angle of 90 or 270 when you're dealing with tan. We call these asymptotes. Okay, so we call those lines x equal to 90 and x equal to 270 asymptotes. Or we could have said theta equal to 90 and theta equal to 270. What else is happening? Well, we can see that there isn't an amplitude on this function. What happens is the graph between 0 and 90 will just continue to rise on and on and on, and the y value will get bigger and bigger. However, there will never be a value when x is equal to 90. Between 90 and 270, you can see that the graph is starting at way down at negative infinity, coming up to 0 at 180 degrees, and then continuing back up to positive infinity, going towards 270 degrees, but never quite hitting that. And again, between 270 and 360, the graph is going down towards negative infinity. So there's no amplitude. And in terms of the period of this wave, well, the period of this wave is actually half of the period of a sine or a cos wave. It's 180 degrees, and you can see a complete wave if you look between 90 degrees and 270 degrees, which is 180 degrees overall. That is a complete wave. So it's from negative infinity up to 0 and then back up to positive infinity. That's one complete wave. At the start, you've got half of a wave at between 0 and 90, and at the end, you've also got another half of a wave between 270 and 360 degrees. So overall, the cos and the sine waves are very different from the tan wave, and what you'll encounter most probably in the course of your studies is the sine and the cos waves.